Yeah, so you might realize that I do not know all the numbers, exact numbers, but I have a general idea about how these geochemical systems work. So you don't always have to have like the exact numbers. You can always find those numbers, but having the general idea about how these systems work, that's, in my opinion, is more important. That intuition that you can develop. But that intuition is not just like a psychic intuition. That is, you don't need special powers for that intuition. You can read something, and when you've read enough, then you kind of like develop that intuition. Okay, so there could be major, what, minor, that, trace, that, something like that. Okay, so you have like siderophile is one group of things that we have. Okay, now if you say, like, let's look at another really simple system, the atmosphere. So let's call that atmophile. So what could be a major atmophile? In core, let me give you some trace. Sometimes you can have silicon, sometimes carbon.
Are we looking like what our atmosphere is made of?
Yeah, essentially. Yeah.
Would be the two number one and two.
Right, noble gases, argon and things like that. It's just that, we just named them atmophile. So the things that tend to be in the atmosphere. So silicon and carbon are sometimes in trace amounts on Earth's crust, but sometimes you can also have sulfur. So if you have sulfur in the core, that reduces the density of the core. Okay, that reduces. So on Mars, we were trying to understand. So there is a way in which you can understand the crust mantle core depth on Mars or the different planets. So say you have like a core, okay? We use a concept called the moment of inertia. Have you heard about this term? So this has something to deal with the distribution of mass around like a sphere. Okay? So if you have more mass centered around the center, you have less moment of inertia. And if you have more mass centered, the same mass, if this is just the distribution, so this gives you the idea about the distribution of mass. So we use both the concepts of physics, because how do we know that any planet is differentiated into its crust, mantle, or core? We don't have, now we have a seismometer on Mars, but we don't have it on any other planet. So we calculate or estimate, we estimate the thicknesses of crust, mantle, and core using this moment of inertia, and it all depends on where the mass is concentrated. Okay, so you have a very solid, if some planet has a very dense core, so its moment of inertia will be less, it's centered around the center. But if it has like a bigger core, but less dense, then the moment of inertia kind of like increases.
Like Mercury.
I do not know what the moment of inertia thing about Mercury, but you might be right. I mean, I know for Mars, because we found out that the core is really big. So for a certain mass of Mars, if the core is really big, so it has to be less dense. Right? So if the same mass is getting distributed over like a bigger area, so it's like you have this chalk which is like really dense. So this same mass, if this is like 10 grams, if this is 10 grams and this is really dense, this is occupying this small space. But if you have wool of 10 grams, that is going to occupy like a bigger, so that is less dense. So we found out that the core is bigger on Mars, and we had an estimate on the mass. So we figured out the density of Mars should be low. And how can you get the densities low? By mixing something which is less dense than the metals. So that could be silicon, carbon, sulfur, even oxygen. But the most likely adulterant, if you may, in Mars's crust, I think, and many people would believe, it's sulfur. So the sulfur could also be, in Earth's crust, sulfur is probably like a trace. It might be a trace. But on Mars core, this sulfur could be a minor, or maybe a major, who knows. So all these different planets, all these different systems, these things will start varying. And also, what is major in one system might not be major in another. So you have to keep that in mind. So you should not think, oh, iron is major, so it's major in everything. No, that's not true. Also, it is not true, is one thing can be a siderophile and an atmophile and a crust loving. And we'll call that lithophile. So litho means rock. What is the rock generally made up of? Silicates and oxides. So basically, the lithophiles will be those which generally form the oxides. So oxide forming. So you can have magnesium silicates, calcium. So magnesium, so Mg2SiO4. And so olivine is Mg2SiO4. See, what is the charge on a single ion of Mg? +2. Cation. Sorry, yeah, cation. It's +2. So SiO4 was 4-, so 2 of these charge neutrality. So Mg2SiO4 is basically olivine. Okay. This is called forsterite, and there is also this Fe2SiO4. This is called phyllite. So these both are called olivines, and they form like a solid solution. We'll look into that. By that I mean there will be. So if you want to write the formula of olivine, you can write, and olivine is basically found in the mantle, the crust and the mantle in here. So olivine should be something like SiO4. You go closer to the core, you start forming more FeMg, so mafic rocks. As you go deeper in the crusts, like this, the FeMg content increases. So you get more mafic and ultramafic rocks as you go in. Okay. So there could be all these oxide forming elements could be like lithophile, rock loving, silicate forming, So Ca, Mg, Mn, titanium, sodium, potassium, some rare earths like uranium, thorium, silicon, iron, and in varying oxidation states. Okay. Atmophile can be so CEO, carbon, O, H, N, S, noble gases. These are basically gases at 25 degrees Celsius or lower than that, the atmophiles. Okay, so many elements. Okay, now there is also a group called a chalcophile. Okay, so there is lithophile, siderophile, and then you'll come across a name called, I have to erase it today, chalcophile. So let me finish on this thing. So the trace is not going to control the properties of, so if anything is in trace, it's not good. So if you have a mineral like olivine, and if something is in trace, And this again comes from the Goldschmidt rules of substitution, the one that we discussed in the previous class. When will some element or some cation, an element or a metal or a cation will substitute something is from those 4 rules that we saw in the last class. Okay, so the sizes has to be same. They can have like a 15% plus minus if the sizes. So if there are 2 elements, and if their sizes are somewhat similar, like just a 15% plus minus, then they'll be easily be able to substitute each other, and that's what is happening somewhat in olivine. Because if there is an olivine which is forming both Mg2SiO4 and Fe2SiO4, then it is likely that some of them at some of these will have 3 Mgs and 1 Fe, or 2 or 2, or 1 and 1, things like that. So it can be 100% Fe2SiO4, or it could be 100% Mg2SiO4, or anything in between, because it's not just 4, right? So this is a lattice, so you'll have millions and billions of all these lattices stuck together. So the percentages, the weight, so the molar percentages and the weight percentages can vary. So if I say, if something is 25 weight percent phyolite, what does that mean? And phyolite is Fe2SiO4. What does that mean? So it's an olivine which is FO25 or FF25 phyolite. If I say Fa25, what does that mean? This automatically means there is FO75, because these 2 percentages should give you 100%. This means that you have an olivine which is 25 either weight percent or mole percent phyolite and 75%. This has to be 7. This has to be equal to. It doesn't even have any doubt just thinking about it. It's fairly simple, right? So it's basically phyolite 25%. That means the iron silicate, the iron part of the olivine is 25%. The forsterite part is 75%. This can also be written as, so this whole thing sums down to 2. So if the phyolite is 25% and this is 75, so this becomes 1.5, this becomes 0.5 SiO4. Does it make sense? Okay, because 0.5 over 2 is 25. Okay, so this is how you will represent, and we call this like a solid solution. We'll see how the phase diagrams and all these kinds of things. We'll use this example, the forsterite phyolite thing. But I want you to realize how this is like a covalent structure, and how the different ionic, the things that are forming the oxides are coming in and they're forming bonds here. Okay. Because Mg2 plus wants to come and form an association with the oxygen, right? An ionic relationship. So this thing is basically, there is an Mg comes here and it needs 2 bonds. So let me, so there's an Mg, it will come in here, and this is trying to form 2 bonds, and so it's kind of like this that will start forming.
Just like a chain reaction.
Yeah.
Because once you produce that oxygen, then you have to produce that big
Yeah.
element of silicon.
So this thing brings in the ionic character. And since ions exist in that lattice, the silicate structure then, so it's like Mg2SiO4 has this covalent character coming from this part and the ionic character coming from this part. And they're like started to form like this. So you can have quarks like SiO2. So what's the shape of this thing? What's the hybridization of silicon? So what's the hybridization?
sp2.
Okay, this, yeah, there's some problem in that explanation.
Maybe sp, wouldn't it be?
According to my thing, yes, yeah, but I don't think this is how,
That would make it linear.
yeah, there's some problem. I'll have to look into that because
So that wouldn't be, because it would be si branches off.
yeah, this is where it breaks my kind of like rule, I think. Anyway, let me look at, because I think this will still try to get this tetrahedral shape, and I'll try to think like how I can, or maybe my rule just breaks in this case, but I'll have to look into that. Okay, but yeah, because this is 2, and this 2 is not getting counted, silica is,
It's linear.
sorry?
It out is linear.
Sorry?
It's linear.
Yeah. So is the structure actually linear? Okay, is it actually linear? Then it's fine. But okay. Then it makes sense, like, okay. Maybe. But I'll have to go and like cross-check once, okay? Okay. This is how like, this brings in the ionic part, and now that whole, the lattice thing starts forming, okay? All right. So lithophiles are done. There's a siderophile. There are atmophile elements, which are just atmospheric. So these are basically gases less than, 300 Kelvin. This is 298 is 27 degrees Celsius. The normal atmospheric conditions. So anything that is like gas in here kind of like fills in this. Now you can have more things. You can have organophile. Okay. You can have organophile. Anything, and these names are just coming up. So you might have heard about these. Lithophile, siderophile. One very important remains is called chalcophile. Does that name ring a bell? Chalcogens?
I can't think of the rock that you never pronounce it. Chalcedony.
No, that's not related to that. That's an amorphous form of silica, I guess. But yeah, chalcedony. That's not that. But yeah, why is it named that? I don't know. Chalcophile. Do you remember there was this group 16 was called chalcogens? Something related to this. So these are sulfide loving elements. So you have all the oxide loving elements here who are forming the lithophile, so the crust, all the oxides. There could be, the carbonate is a kind of like an oxide, so it's still forming bonds with O. But in sulfide, there is no O. Sulfate, there is an oxygen. Oxides, of course, carbonates. But in sulfides, there are no oxides. The sulfide is S-2. So you have lead, anything that forms a sulfide some iron sulfide. This is pyrrhotite. There is, or troilite sometimes. So these are iron sulfides. This is a lead sulfide. There are copper sulfide. And why are these sulfides important? I mean, that's their property. But imagine, I don't know, how many years ago, 1,000 years ago or something, why would you be interested in certain earth materials over something else? Metallurgy, basically. So if you can extract the metal from these, extracting a metal from an oxide is challenging. So aluminium was really challenging to extract because there are no aluminium sulfides. Extracting metals from sulfides is easy. I'm not going into that. It's a reactivity idea. But oxides are really stable. They're really less stable, really more stable, less reactive. These are, so we can easily extract metals from them. So all the that's why in metallurgy or in the prehistoric, historic times, we were focusing on these sulfides because it is easier to extract iron from this or copper. What's this called? Copper sulfide? So this is galena. This is HGS is cinnabar. What is copper sulfide? I don't know. It's easier to extract copper from here than a copper oxide, CuO. This is cassiterite or something like that. And that is why this is important, because this is very stable, this is not that much stable. And that is why if it is more, and why do you think this is more stable? I mean, why? It's an oxide, O2 minus versus S2 minus. So you have an O2 minus, S2 minus, which is more stable? It's the same group, right? So it's group 16. So it's oxygen. So this is forming a -2, -2, -2. I'm saying that O minus 2 is more stable. Why is O minus 2 more stable?
Less shells.
Less shells, yeah, true. But why is it more stable? Yeah, true, it's less shells. So? I mean, I'm going to give this question in a test, right? Because it's, you can get to the answer of this from the things that I have taught.
Does it have to do with hydrogen bonding or?
Think about electronegativity.
This is at the top.
Yes, so it has less electronegativity or more electronegativity?
That's right.
So electronegativity increases and decreases. So oxygen is on the top, so it has more electronegativity than S. So it's more electronegative and it has a negative. So will it be more stable or less stable? I am more electronegative. So I'll be able to keep that minus or be perturbed by that minus. I'll be able to keep it because I am more electronegative. Just see a very different case. So imagine Na plus and O2 minus. Okay? If you have Na minus and O minus, which is more stable, Na minus or O minus?
O minus. Because the electronegativity decreases as you get to the metals.
Right. So in any case, Na minus is not a stable configuration, first of all. Even O minus is not a stable configuration, but still it is better than Na minus. Okay. Keep this thing in mind. Electronegative things will be more happy when they are negative, less electronegative things will be more happy when they are positive. Let me repeat that again. More electronegative things will be happy when they have more negative, and less electronegative will be more happy when they have less negative. It's simple. Also, less electronegative will be more happy when they're positive, like Na+. It's like less electronegative or positive. So in this case, oxygen -2, so oxygen being more electronegative, it was able to keep the -2 charge, no problem. But S-2, if we compare them, although S-2 exists, but if you compare the stability, S-2 is less stable because it's less electronegative. Does it make sense? Okay? So that is why oxides will be more stable than the sulfides. Does that make sense? The oxides are more stable than the sulfides. Does it make sense? Okay, so the oxides are more stable than the sulfides. We have established that. Now, if the oxides are more stable, will they break down and give you the metal? Or it's more likely that the sulfides will break down and give you the metal. So one thing is already, so the thing which is more stable is less likely to break down. The one thing which is already less stable is going to break down easily. So in this case, the sulfide is less stable, and that is why it will break down easily. And therefore, extracting the metal from the sulfide will be much easier than extracting the metal from the oxide. So that is why this chalcophile thing is really interesting, because we need to find out which metals are chalcophile. So we can directly go to those sulfide. So if you want to, let me write down some chalcophiles. Copper, lead, zinc, cadmium, molybdenum, mercury. What is this? Tellurium. Antimony, yeah. It's a stibbium antimony. Group 15. So copper, lead, zinc, cadmium, molybdenum, mercury, these are all D block. This is group 15, group 14, tin, carbon, silicon, germanium, tin. Tellurium is 13, it's boron. Tellurium is? I don't know where tellurium is. It's group 13 probably. Boron, aluminium, gallium, indium, thallium. Yeah. Is it 16? 16 is this. Oh, Te, yeah. Te is here. I'm talking about this. This is thallium. Sorry, this is thallium. This is 13. 13, yeah. And this is arsenic, group 15. So you see there is a range of. So it's a reason why we said group 16, like those are the metals that are forming chalcophiles. So now if you're in the mineral, like metal extracting metallurgical industry, so if it is more likely that if you're extracting a molybdenum, you will go to a molybdenum sulfide, you will try to find a molybdenum sulfide ore deposit than a molybdenum oxide. Because first of all, it will be easier for a sulfide to break down and give you, because of obvious chemical reasons. And we know that it's chalcophile, so it's likely that you'll form this. But if there is a lithophile, so if you want a manganese to be extracted, you won't go and look for a sulfide, manganese sulfide deposit, because it might exist, but it'll be rare. Because manganese, when it is forming, it's more likely to become like a lithophile rather than a chalcophile. Okay? Interesting. Now, some things can